Hello, welcome to the last part of the memory management portion of the OS course. We will be covering two topics here, page fault, or which is an implementation of demand paging. Then we'll go into multi-level pages. It's going to be a repetition or maybe a revision of what was taught in part 3. So I would expect you to go through this memory management videos in the same sequence, because I would be assuming that you know certain things which have been covered in the previous lectures. So this is a very good quick recap of paging. We know that this is the logical memory, and any page number what is given here is going to be used for indexing into the page table. And the content right now, we are assuming that only the frame number is there, which is nothing but the frames here, and whatever is the page size here is same as the frame size here. And whenever a program is executable is opened up and is going to be executed by the program as a process, its pages are available, and OS keeps moving across main memory and the hard disk based on the replacement policy and the need for a frame to be moved out to a hard disk for various reasons. So given this introduction, let us just quickly go through this. We have to assume, because none of the picture doesn't say what is the page size here, so we are assuming that the page size is 1 kilobyte. In that case, you should immediately, it should come in your mind that it is 1 capital KB is 1024 bytes, and the number of bits required for accessing 1 kilobyte or 1024 bytes of information or a page, it needs 10 bits. So 2 power 10, 2 to the power 10 is 1 kilobyte. Now process P1 is shown here. It needs 8 pages of 1 kilobyte size each, and different processes may have different requirements. So the logical memory number of pages will be varying, but it again depends on the width of the logical memory address space designed by the processor is a limit. Okay, within that the process can use part of it or full available virtual memory or a logical memory available in a system. Now page table is there, which is mapping the P1's pages to the frames. Every process will have its own page table and their mapping will be different, but they all map to the same physical memory, but it may be pointing to different frames in the physical memory, but the entries of each page table will be actually corresponding to a frame number of the physical memory you have. Now what is the frame size? It should be same as page size. And what is the offset bit? Just now told, to access 1 kilobyte of page you need 10 bits. What is the logical address bits of P1? Now total number of logical address bits, because it has 8 pages, it needs 3 bits. 2 to the power 3 is 8, and 10 bits are required for accessing each of those pages. So 10 plus 3, 13. Now what is the physical address bits? Here again the physical address bits are more than the logical address bits. Okay, normally the logical memory size is bigger than the physical memory. It doesn't matter. Given a problem, what is the number of bits required? There are 16 frames, that means 4 bits are required for accessing each frame, and again page size is same as frame size, and which is 1 kilobyte, and again it is 10 bits. So 10 plus 4, 14 bits is the total number of physical address bits. Now what is the process P1's memory size? P1's total memory size is 8 pages are there, 1 kilobyte each, so 8 kilobyte. Physical memory size is 16 into 1 kilobyte. That's just it. So if page D is brought into the frame number 13, suppose if you are bringing page D, remember each of the pages are indexed by using the page number. So if D is to be brought into the page table, it can't be brought in any other location. It has to be the third here only. Okay, and it is brought into the frame number 13. So we are assuming that it is going to be here. Then what will be the entry here? It will be 13, and this I will become V, because that's a valid bit or present bit. Since that frame is brought, page is brought into this frame, we have to give the frame number. If page A is moved out, I am moving out page A. Okay, from here, where will I move? I will move it here, and it will be copied if dirty bit of this particular frame is set. That means if it is modified, read writable, and it has been modified by the program while it was using this page, so the dirty bit or modified bit is set. So if I am moving this page out for some reason, maybe to bring some other page of some other process or same process, we need to update the page table of that particular entry of this entry here, whichever process is owning this particular page or a frame where page is being held. And if dirty bit is set, I need to write it back. If it is not, then I can just replace it with a new entry, but I need to make sure that the page table entry is modified. So where is A here? A is in the first entry and it refers to this page number. So I need to make this entry maybe empty, because I don't have to do anything, because even if I make it 0, 0 is a valid number, right? So even if I make it 0, it's a valid frame number. So what I need to make sure this I is done. The previous entry can be there, because if I make it invalid, it will the OS will not even look into the entry of this. Okay, so that's what I mean by I. Suppose the lower 4 frames are used for OS, and then I want to, can the entire process P1 be accommodated within the memory? Yes, there are, apart from 4, no, if I take away 4, 12 frames are there, but my process is needing only 8 frames, and I am assuming that no other process is there except OS, and OS is happy with the 4 frames I have. Then it is possible for P1 to be completely brought into the memory. Okay, that's what is the question 4 is about. Sorry, 3. And if another process P2 enters the system, will this page table above be used? It is not. I just now said that each process has its own page table. Okay, that's it. So let us go into PTE, which is page table entries. We said that it has got modified bit, access permissions, read, write, executable. These are all the present bit are there. Now there are some other finer control bits are there which are related to cache. When I say this cache, it is L1 cache, L2 cache, L3 cache, but we are not going to be covering this as part of this OS course. We will cover it up in a process architecture course. Now what are the other control bits we have covered earlier? Modified bit or dirty bit, which indicates that a particular frame where a page is residing has been modified by the program while it was accessing that page. Okay, it may be belonging to any process. It has to be owned by a process, so it is modified. That means if I am replacing that page, okay, or that frame where that page is with another page from either same process or different process, I need to make sure that this page is written back into hard disk, which I just now explained. So if no changes have been made, then I can just replace it with a another page. Present bit indicates that in a page table entry, if there is a present bit set, that means that particular page table entry is valid. Whatever frame number is there, whatever modified bit or read write executable access permissions are there, they're all valid because that page is present. If it is present in the main memory, that means it is a valid entry. Okay, because any page which is present in the main memory should have an entry in its in its own process table. Okay, each process has one page table and it should be there. That entry should be there in it. Okay, so if the page is not there in main memory, then what will happen? There will be a page fault, and then it's called demand paging, and the particular page is brought from the hard disk to the main memory, and the present bit is set. Okay, and then based on what you are bringing in, whether you are bringing code or a data or a constant data, your read write access permissions will also be modified. So that information is there when the program is brought into the main memory, the resident set. Now what about read only bit? It is that particular page cannot be modified. Okay, if suppose the process tries to modify it for some reason through because of illegal pointer or something, then there will be an exception created, generated. Exception means the program will be stopped and the OS will get the process. The process will be terminated and it will be notified. The process will be notified that it actually made to violated the rule. Okay, so what are the page fault? Page fault is, I said that when you are executing a program based on the need of the program, the particular page is brought. That's what is called demand paging. Now, when will the page fault is generated? The page fault is generated when the particular page is not present and the program wants it. Now, what is the action to be taken by the OS? It is to be brought from the hard disk to the one of the frames in the physical memory. If all the frames are occupied, everything is filled with some pages from different processes, then there will be a page replacement algorithm. There are two at least we will be covering, FIFO and LRU. I'll talk about what they are. And then based on that algorithm, that particular page will be taken out. Okay, from one frame will be identified in the main memory. A frame will be identified. Okay, and then it will be moved out. If it is fully occupied, means this frame is also having something, and if the dirty bit is set for this particular page, then it will be written back. Otherwise, can be overwritten with a new page, and then whatever caused the page fault will be restarted. The instruction will be restarted. Okay, that's what is there. Now, what are the possible reasons for triggers for page fault? It is for loop is going through and accessing something which is not there in the memory, or it is initially only the pages or the initial locations are brought and the remaining things are brought in based on the need. That's called demand paging. Now, what is it? It's a method of virtual memory management in a system that uses demand paging. The operating system copies a page from the disk into physical memory only if an attempt is made by the running process to access it. If suppose for some reason a particular page is not accessed at all, then it will never be brought into the main memory if it was not initially done. So it is brought only when it is needed, which is called demand paging. Advantage is it uses the memory frames, main memory frames efficiently. Okay, only the required pages are brought for every process. So many processes can share the system and they can still be running without any problem. But what is the problem with the demand paging? Whenever any new page is required, it's not available. It has to be brought from the hard disk, so the program will be stopped. So there will be a efficiency, running efficiency will be affected because of frequent stops based on the pages which are needed to be brought always, because it's not all the pages are not brought loaded in one go. So now how do you decide a page size? Okay, page size, I said that it can be 1 kilobyte or maybe 4 kilobyte or 8 or maybe some megabytes also. Okay, some systems have. Now how do you decide what is the optimum page size? Now you have to think from two perspective. Now suppose the requirement of a process, the logical virtual memory or logical memory is fixed. Already the program, you have decided the size of your variables and the number of functions you are writing, how big your functions are, how many files you are including, or libraries, static libraries you are including. So the size of your program is decided by you when you are building an executable. Okay, you are not going to decide the size of the your program based on the page size. Now page size is decided by the OS based on whatever reason it has. It has a physical memory and it has to decide that okay, this is going to be my page size, and I am going to have a MMU which is going to be configured for a particular page size. Now assume that I have used very less with less number of bytes for a page. Now your size is fixed. Now if I am dividing, if I am deciding the page size is small, I have to divide multiple times your logical memory space, and then for each of those entries I need to have a page table entry. So your page table is going to be huge because number of pages are going to be large, and if page table is large, you have to store this page table also in the main memory. Okay, but it is not part of the process. It may be part of the OS. So the page table needs to be residing in the main memory, and if the entries are more, it is going to take more time to index into the page table and access them. Okay, so lot of memory space for the page table as well as access is going to be longer. Okay, and then one more thing, what is it is because of optimization done. It's not a general just addition. Okay, so now what happens? What about on the physical memory side? That is also going to be divided into small regions. So internal fragmentation will be smaller. Okay, but you are to, if suppose you are moving in some page and moving out some pages, you have to write small chunks into the hard disk. See, hard disks are block devices, and they are all optimized for a bigger size of um, memory to be written or data to be written. It's like you run a big bus with which is 60 seater, but there is one person sitting in the bus, and it's a inefficient way of sending the bus on the road, right? It's going to occupy more space. Similarly, if you are transferring only a small piece of data into the hard disk every time you are reading and writing, it's going to be expensive. So that's a inefficiency part of it. So you cannot decide your page size to be too small, because your page size will be larger and block device accesses will be inefficient, because it is normally it's designed for a larger chunks of data to be written into the hard disk. Now, what is the other way around? Let me now go to the other extreme, that I will make very huge page sizes. Okay, maybe my total logical memory is divided into only two. Okay, I say that this is 16 MB of one page, if I am deciding. Now, your physical memory is going to be divided in a very big areas. Okay, I am going to divide it, now hardly I will have few frames in the whole main memory. In that case, if my frames are limited, how many process can be running there? I will be having limited number of frames for me to play around with. So there will be frequent swapping in, swapping out of huge frames. Imagine if a particular byte is written, a dirty bit is set for a particular frame. Even if there is a byte is written into a particular frame, I need to transfer the entire frame into the hard disk. I don't know where which byte is modified. Then it's going to be taking lot of time writing huge data also. So, though block devices are optimized for larger data, if I am writing very huge pages back and forth from the hard disk, it's going to be inefficient. So it's not going to use the main memory efficiently. Multiple processes cannot be running in parallel, and hard disk access will be inefficient. So these are the problems, and then you need to choose an optimal page size that is not too, it's not falling in the outliers, it's somewhere in between. Okay, this is what is explained in this particular slide. You can run through this, you go through it, and whatever I have told will be is available in the textual form. Fine. So now we are going to change gear. What is multi-level pages? Now, what? Let me at least tell you. Suppose if I have a process virtual space, and this is the ROM area, which is read-only code, read and executable permission is also there, and data area, which is read-writable, and then I have a stack. Now, what happens is, most of the time the heap what I need initially will be small, and then it will be growing, and then what I need for the stack also initially is to be small, and then as I keep calling functions, the stack size will be growing. Now what happens is, though my logical memory space is this much, I am only using only this pages, maybe couple of pages here. The remaining things are all empty now. As and when it is required, the pages are, entries are made in the page table entry, and those frames are reserved, and you are you start using it. So this is how the requirement of pages grow. So initially the size or heap of the heap or stack will be small, increasing in size, and slowly they increase in size. Then table size comprehends, but you need to comprehend the page table for the entire address space. You cannot say that no, anyway this is not there, so let me not keep a space for the page table. I need to keep it and then make it invalid. Okay, all these bits are invalid because they are these pages are it's not even used by the program, and it is not even available in the main memory because you don't have to load them. Okay, so what happens is, the virtual address space whatever is given is huge, and if there is a only single level of page table, then I need to have that many entries there in the page table, whether I am using all the areas of the virtual address space that I have or not in a program. So that's an inefficient way of using the page table. With a single level page table, this is the problem. But suppose if I have one level of page table, okay, I will tell you how it is being divided, and then that refers to another page table, then which refers to actual page. Similarly, here also is refers to another page table which refers to this page. Now just for a moment think about it. We are grouping, you can see this page table is going to refer to so many of small pages. So suppose there are 1, 2, 3, 4, 5, 6, 7, 7. So 7 entries are there, which normally it will be in the number of 2, power of 2, but it's okay. The number of entries need not be no order even, but I don't assume no something, no some numbers are there. It will be normally powers of 2, okay. And now maybe this picture should have been modified. Assume that there are 8 entries, okay. This 8 entries are there. Now each page size I am calling as 1 kilobyte. Now this page table is responsible for how many pages, actual pages were 8 1 kilobyte pages, okay. I am assuming that there are 8 entries. Then this page table is responsible for this page table is referring to multiple of this size. So let me first talk about this page table. This is responsible for 8 kilobyte. Okay, agreed. Now, what about this page table? Okay, I have a first level of page table and the second level of page table. This page table, each of the entries here actually refers to 8 kilobyte. Similarly, there will be this many. Okay, assume that there are 16 of them. Now, 16 into 8 kilobyte is the total size of this particular page table. So, as you move closer to the actual page, the page table is going to be only responsible for those pages, number of page entries and the page table. But if you go away from this first level, second level, third level pages, then the top level page tables are responsible for the huge number of all the pages underneath. Okay, it's like you have a directory, subdirectory. Suppose you have a C drive, then you have multiple subdirectories, and each of them is occupying maybe 10 gigabytes, or this is 2 gigabytes. Then the size at this level is the sum of all this, right? And then you go deeper into this. On this directory has only some 10 kilobyte of data, then this directory is only responsible for 10 kilobyte. So you can imagine the same thing is true with the page table also. So two level page tables, what is the advantage, I'll tell you. But before that, you should know that the page table which are closer to the page actually corresponds to smaller number of pages responsible for that. But higher level pages, all the pages coming under them will be they refer to that. Okay, so larger pages consisting of set of smaller pages. Okay, that's what I'm saying. The higher level page tables will be responsible for larger pages. So now if you have a single level of page table, I said that indexing will be too many because all the page numbers are there in it. But if you divide them into two, then number of entries of each of them will come down. And I will show you with an example, then you will be able to understand. The multi-level paging system simplifies its implementation, okay, by you having indirect blocks. Now, let me give an example. Now, suppose given this division, okay, that this is the virtual address, total virtual address, which is divided into this. Now, how do I know number of bits that each of them is occupying? Now, this L1 offset is referring indexing into this page table, which is a first level master page table. Now you see the entry 10 to 4095, that means 4096 entries are there, which is 4 kilobyte. Now 1 kilobyte takes 10 bits. Okay. Now 4 kilobyte will be taking 4 into 1 kilobit, right? So that means for 4 combinations you need 2 bits. That means 2 plus 10, 12 bits. So this will be 12 bits. Okay. Now what is this L2 offset? It is referring to this page table entry which has got 256 entries. 256 entry is very straightforward. You can say that 8 bits, right? 8 bits are required to represent 256 individual entries in the page table. Now what is the page offset number of bits? It is already given. Bits are 0 to 11. That means 12 bits are there. So totally 12 plus 8 plus 12. Okay, 24 plus 8, 32 bits. Totally it's a 32 bit address. So this is how the page tables are referred. Now whatever this is a particular page you are referring to, and then this entry actually gives you an index, or actually this is the base address you are having, because each of those entries will have the base address of the page table, because second level page table address is stored as a part of the page table itself, and then you have the offset which is coming from here. So you are getting the beginning of the next page table, and then you get the offset value to index into this page table to get the entry. Now again, it is a frame, starting of the frame. Remember, an entry in a page table either refers to a final physical frame where it is starting, or it is going to have a base address of the next page table. Okay, if it is a not the last level page table, then it is going to have the base address of the next level page table, and the index will come from the next entry. And then access permissions will also be there. Okay, last one will have the access permissions. Okay, you don't need to have the access permission at this level, but you need to have here, because that's what is currently finally refers to the frame in the main memory. Now, why are we doing this? Since I said that at this level it is going to be multiple pages, right? You imagine this is a 4 kilobyte page and 256 entries are there. 256 into 4 kilobyte is the size of, okay, one entry here. Okay, one entry actually corresponds to 256 in 4 kilobyte entries. Okay, so that actually means this and this. Okay, the 4 kilobyte comes from this 12 bits, 256 coming from this. So 8 plus 12, whatever is remaining on this side is the size of every entry of this higher level page table. Okay, so whereas if you only refer to this page table, it only each of the entries are referring to only 4 kilobyte. Okay, so that's how you have to see that it is the higher level page tables actually refer to a responsible for a huge number of pages. Now, if I have empty entries here, then the entire 256 into 4 kilobyte of space is not used. So what I am doing by not having an entry here, I am saving the entire space required for a second level page table. So because the page table entry will be huge only at the last level, because modified date, present date, and then read write executable permission, and remaining many things are there, information about cache and other things. So if I save a entire page table of the last level, or maybe even the next previous level, if it is a 3 level or 4 level page table, then I'm saving a lot of space. So there may be some holes in the logical memory. As I said, that heap and stack are going in between, there are holes. Similarly, wherever there are holes in the logical memory, the entry of that will not be there, and you are saving a lot of space in terms of page table itself, and then accessing also will be faster. So it is most efficient way of handling paging by having multi-level pages. That's what I am trying to convince and tell you. So I will talk about the TLB soon. Right now, let us not worry about it. So this is the summary of what I want to say in a page table and multi-level pages. So let us stop here and then go to the next. This is done. Okay, 7D is done. So let me move to 7E. I'm going to be a little faster here, saving time, because you already have learned a lot of these things. Now the same picture is coming, so I don't need to tell you anything about it. I mentioned about TLB. What is TLB? Okay, we will come to that soon. Okay, it's actually a hardware cache, associative memory cache, and it is inside the CPU. Okay, translation look ahead buffer. Actually, it is having an entries of a page table in. Okay, actual PTE is kept in the hardware. Now let me tell you how it is improving it, the performance of the program. Now another example which you can actually practice by looking at it. Now I have given the number of bits of different levels and the final level. You can make out that this is 4 kilobyte byte, and then how many entries are there in the second level page table. Just 10 bits are there, 2 power 10, and first level page table will have 2 power 10. Again, both are same, but this each of them will be responsible for how many pages. Then you can easily, one entry here actually refers to these many 4 kilobyte. Okay, each of them are 4 kilobyte, right? Second level is offset is 12. So 1024 into 4 kilobyte. Okay, is the total size this particular entry is referring to. Okay, now you can actually backtrack and then suppose if I am giving you an address like this, how will you know? Okay, this values you need to write it in the binary form. So remember, hexadecimal to binary form, you have to be very clear. Now this 00, each 0 is corresponding to 4 zeros. Okay, and then 4 is there, 0 1 0 0. Okay, let me draw like this. 4 again, 0 hexadecimal, and then 3 is there, so 0 1, sorry, 0 1 1, and then again this is the number we have written. Okay, totally this value virtual address. Now 12 bits I need to have a partition, so let me take another color. 12 bits, where is it coming? This is 4 8 12, so 3 into 4 12. This is the offset area. Okay, offset area. Now 10 bits I have to count. Now this is 4, this is 4, so I have to divide it here. Okay, this 10 bits, and of course you will have a remaining 10 bits, 8 plus 2 10. Now what is that value? Here I get all 0 0 0 3, right? So that's why 3 is put here, and here 4 is there, that's all. Okay, so this is 4. Okay, this entry is I think here this 4 is given. Okay, this value is 4 and this value is 1. Okay, this is how hexadecimal value you have to put it into decimal form, binary form, and then divide it based on the bits, and then you can find out that given a virtual address I need to keep this 4 intact. Okay, offset value 12 bits has to be intact, and this is giving me a value 1 is being used. Okay, let me now okay, let me not erase anything. Now you see here, this is value is 1, so it will refer the one first element, second element, and it has got 54. Imagine that 54 is the base address of this particular page. Okay, and then I have to add something. What should I add? The value 3 here. Okay, so that is why third element is taken and 312 is coming. Now this 0x00312 is nothing but the frame number, and then I have to add the offset value, which is nothing but 8 zeros. Okay, and one more 0 1 0 0. Okay, okay, I'm not, sorry, 1 0 0. So this will be the total physical address that I will get. So you have to have a clarity on this particular thing. I hope this is clear to you how we are dividing it, and the base address is taken from there. Now this is the bit pattern and we are dividing it like this, and physical address is this. Okay, this is how physical address is taken. Okay, that's all. We are not going to go deeper into this. Now I'm going to just give you an example of a 48-bit logical address. Now inside an ARM processor, a 48-bit page, logical address is divided into how many pages, levels. Okay, this is 1 2 3 4, 4 level pages. Okay, 4 levels of page table, and this last page table is only is referring to the actual frame. So you will get the physical address and this frame. Okay, offset is here. This frame number you will get it from this entry. Okay, this is where this PT is there. Okay, and it actually refers to the base address of this page table, and offset will give you the frame number. Okay, so you get the actual physical address from this page table. So this is actual 4 kilobyte page, and actually this is the address you are accessing. Okay, this is the actual page, physical page. I am showing only one frame. Okay, the entire main memory is there and one frame I am saying, and then this offset is using the address. This is the 4 kilobyte of page. Okay, and this you don't need to worry about it. You just I'm showing you that actually 48-bit is used for accessing the logical memory, and but they are divided into multiple pages and multi-level pages, and this is how it is being done in a 64-bit processor. Okay, and now what is happening is logical address space is 64 and the physical address space is 52. Okay, that means what, I am using only the 2 power 52 size. Maximum I can have a physical memory of 2 to the power 52. Okay, that itself is huge. Okay, now suppose if I give you logical memory size, or it could be that I give the bits and then ask you the size, or size I give you, then you convert it into the address. So suppose if I say logical memory size is 256, immediately it will strike you that it is 8 bits. Logical memory 8 bit address. Page size is 8 bytes. If I say only 8 bits are the page size, that means how many bits are required to represent 8 different values? 3 bits. So offset value is 3 bits. Now physical memory is 128 bits, means 7 bits. 7 bits, 2 power 7 is 128, so 7 bits. So these numbers you should be having clarity. Then you will be able to find out what is the page number and offset, because you know the offset number. Okay, offset value, you know that totally logical memory is taking 8 bits, out of which 3 bits are gone, then page number will be 5 bit value. So what are the maximum number of values? 0 0, okay, to 5 ones. Okay, isn't it? So 32, 0 to 31. Okay, and then what about the frame number? It is 128 bytes are there totally. Then you are knock off 3 bytes, that means 7 bits are there totally, out of which 3 is gone, so you will have 4 bits for the frame number. So number of frames are 2 to the power 4, 16 frames. Okay, so can I guess these values? Yes, because already I have given page size and frame size. Other sizes are already given. Now, what about the number of pages? Okay, number of pages in the page table. How do you find out? Number of pages in a logical address is, if I have 5 bits per the page number, 2 to the power 5 number of pages I can access, right? So it is 2 to the power 5 is 32. How many frames? 2 to the power 4. Frame number is 4 bits are given to you, so 2 to the power 4. So it's very simple binary arithmetic and binary numbers. Maybe suppose if I give you value 0x7a, and then if this particular address is generated, logical address, okay, imagine whatever address is generated by the CPU is logical address. Now what is the page it is accessing, and within the page what is the offset? You have to divide this. If it is given as a logical address, then you have to go by this division, right? 3 bits, so 3 bits I divide. Okay, this one, so 2, value of 2, that means third byte in the page, or a page only, because, and then this is 15. Okay, so what is the page number? No, page number is 15, but this is a 16th page. Okay, last page. No, it's not large page because 5 bits are there. I'm only using 15, so its number is, page number is 15. I hope this is clear to you. Now, what is the page replacement algorithm? When are we going to use the page replacement? When the entire main memory is filled with lots of frames and some new process is coming and it wants some space in the main memory, or the existing process which is running is asking for more. Maybe stack is growing, or maybe it is accessing some other data which is not currently present. Page fault has come. The demand paging means page fault will happen, and because of that a new page has to be brought. Now when I want to bring a new page and I don't see any frames free, I will move the frame out of the main memory. Now which one will I choose out of the existing frames is what is the algorithm, page replacement algorithm. Now which one I am going to replace? How do I decide that? That is the algorithm that I am going to, some algorithm I need to use to choose one of the frames to be evicted out, which is called a victim page. Now it will come when page fault happens for a new existing process, or a new process is entering system which is having some requirement of few pages. Then I need to find a space in the main memory. Now there are different algorithms are there. There are two, at least we will talk about it: FIFO and LRU. What is LRU? Least recently used page. So which is better? We'll just look at it. Now what I'm saying here, I'm giving a sequences of page numbers, okay, being referred, okay, and they are residing in a frame. Now, how many frames I have in my main memory? There are only 3 frames, remember, okay, that's all I have. Remaining maybe OS is using, I don't care about it. I have 3 frames. And imagine that initially a page number 7 of some process is accessed, 7 is residing there, and these two are empty. Then I am accessing 0, then 0 is brought because I have a empty space here, so I don't need to do any replacement algorithm. And then I want to access 1, yes, 1 is brought here. Now suppose after all these 3 frame pages are brought in, the process wants a second page of its own logical memory. There is no space now. All the 3 frames are filled. I need to evict something. Now, which one did I evict? The picture shows that now 2 is sitting here. That means what? 7 is evicted. Now, was this frame written back or not? You don't know. If it was modified, then it would have been written back. Otherwise, it would be just replaced. Now, how did this decide that out of this 7 and 0 and 1, these are all page numbers, it chose the 7? What would have been the algorithm? You know, this in the time sequence, this is the time, 7 came first. So I am going to replace the 1 based on the FIFO algorithm, first in, first out. Whichever page came in, and which is residing in a particular frame, it happens to be in the first frame, okay, or 0th frame, 1 frame, second frame. So it resides, the 7th page is residing in frame 0. I have evicted it because of FIFO algorithm. Now, next access is 0. It is already there, so I don't need to. If I'll call it as a hit if I am accessing a page which is already present in the main memory. Now, next I want 3. Is there 3 available here? No. 2, 0, 1 is there. 3 is not available. Now, which frame should I take out? 2 came in recently. 1 came prior to that, but 0 came the earliest one. 0 is the one which came very earliest. So that out of this, who came first? 0 came first. After that, 1 came, then 2 came. So I need to pick up 0. Okay, I am removing the 0. Okay, either I am writing back or whatever. Then I am writing the 3 here. Now next I am accessing 0. Immediately I want 0. Now 0 is not there. I need to bring it. Now I will pick the victim page as this one because this was the one which is the oldest among the pages which are there. So this is how the remaining things are filled. I want you to look at this remaining entries as a practice to see which are the hit and which are the misses and which frame is getting replaced. So that's a homework and it's very simple. It's like a puzzle, an interesting puzzle of course. So that's done. Now to start with, which page was brought in? 7, and then I have explained it already, so I don't want to spend time on this. Now, what are the problems or what is the advantage of FIFO? OS maintains the linked list of all pages, 3 pages, and then whatever was filled, the earliest one, which is going to be overwritten. Now, what is the disadvantage of this? Page in memory that has been there for a long time. Okay, a page is there for quite some time. That means what? That maybe that process is running and it is being used. Okay, maybe it is residing there means it's like some tenant is there in a house living for long. You say that if somebody is living for 20 years, 30 years, then the place belongs to the person. Okay, I'm not saying that your tenant will say if he or she is living in your house for 20 years, the house belongs to me. But normally, this is how the some of the countries decide about the citizenship of a place. So the page has been there for long in a frame, then it is being used. Then why do you pick up that fellow and then throw it out? Okay, that then what will happen is suppose you are using you are picking up a frame or a page of course to evict it, which is being actively used. What will happen? It will be immediately used. Okay, it will be accessed. Page fault will be generated and you bring it back. That's what happened in this case, right? 0. So I will give you one example where 0 was evicted, but immediately after second access 0 is asked for. Then I am bringing it in, right? Bringing the page in. So it is going to be expensive in terms of page which is active is being thrown out, and then it is again page fault will come. So too many page fault will happen because of this FIFO thing. So repeated page faults may happen. So FIFO could pick a wrong page which is still being used by the program. So you understand the remaining thing I told you. Now, what is the best thing? Maybe least recently used. Now, if I am using least recently used page for a replacement, imagine the same accesses. I'm having 701. Now, I need 2. Okay, sorry, 2 I need. Now, out of the 701, which one should I pick up? Now, 7 was used and then 0 is used, 1 is used. So, 7, see, this is the page access sequence. Okay, so least recently accessed page is of course 7, right? So I am replacing 7. It is same as FIFO. FIFO also, you may wonder that FIFO and LRU are the same. No, I will give you an example where you will understand the difference. Now, after this, 0 is accessed. No problem. 0 is here. Okay. Now, 3 is accessed. In our FIFO algorithm, if you recall, if you remember, maybe you can go back in your slide and then check. 0 would have been picked up to be replaced to bring 3 in. Okay, but we are not replacing 0, though it came in first. FIFO, as per the FIFO algorithm, 0 came first. Okay, I should have picked up, but I am picking the 1 to be thrown out. The reason is 1 was accessed much before the 0 was accessed in time sequence. Least recently used is this. Okay, out of all the pages which are there, let me explain you once, because this is little tricky to understand. See, I want page 3 which is not there currently. Okay, look at it, it's not there. Now I need to choose the victim page. Which one should I choose? Can I choose 0? No, this is recently used. I will not use this. I will pick up this. Okay, I go back 3. Why should I go back 3 times? Because these are all there in this exactly in the frame. There are totally 3 frames. I can't go further down. Okay, I need to use, maybe you may have the same access. Okay, same pages may be accessed. Then I might have to go little further. But access sequence is like, luckily or unluckily, you have different pages. Okay, every time we are not accessing the same page in a sequence. There is always, it's not that this should be happening like this. So I will not pick up 0 now, because to accommodate 3 I'm not going to pick up 0, or I'm not going to pick up 2. I'll pick up 1. So that's why 3 is sitting here. Now I want 0. Okay, fine, and then I want to get 4. Now again you see the 0 is lucky, because it was accessed recently. So I will not touch 0. I will not touch 3 also. Of course I will not touch 0. I told you that when I am going back, if I encounter the same page which is coming again, I'm not happy with this. Two candidates are accessed recently, so I need to go to the last fellow, which is a third candidate, which is 2. So I have to refill this guy with 4. Okay, this is how the replacement of LRU works. Remaining things, you please understand it yourself. Now if you look at the way it is, the same sequence is given, but LRU actually has more hits. Okay, these are gaps or hits, misses are these entries. Okay, so you get more hits when I use LRU. So LRU is most advantageous, and it is actually reasonable also. Recently used pages, that locality of reference says that if I use something, I am going to use the page around that. Imagine a page is not a 1 byte, it's a 4 kilobyte or 2 kilobyte or maybe 8 kilobyte also. So if I have accessed the page, one of the 4 kilobyte I have accessed, I am likely to access some of them, even with the time. So, locality of reference could be time based or space based. You may be accessing it. So that's why LRU is the best algorithm. How do you do this actually? Which was accessed, every may access. See, imagine this is not the, I'm showing you as a page access, but it could be one memory access in a page, or it can be multiple accesses within the page. So I need to keep on, updating my time. What was the latest time at which time stamping of accessing a page? So I need to maintain a timestamp of each frame It's not a page actually, each frame, because I am looking for a candidate with one of the frames, and then I go to the page table entry of that particular process and then remove it. So I am maintaining it frame wise. Remember, what was the timestamp lost access, when was it this frame was access lost. But page number actually brings you to that frame. Actually we are maintaining it with respect to the frame, because our aim is to pick the one of the candidate out of three. So you have to maintain time wise stamp of a frame being accessed. Whenever it is accessed, you update the time. Now you go and look, if you are looking for a candidate, look for the time which is the longest, farthest from the current time, and pick that particular frame, throw that page out, okay, and bring a new page into that page. Okay, this is the replacement policy of LRU. So this is done. Now we are going to only see one more concept, which is called TLB. Now what is TLB? When you have multi-level, okay, paging, here I am showing you only one single level, but actually it will be more efficient when you have multi-level page table, because given an address you access multiple pages, you go here, access the page table, and then add this offset, okay, and then access another page table, then take out this offset, okay, sorry, it should not come here, it should come here, and then offset is here, so I take this plus you do, and then page table, then I access the finally frame number I get, and then access the frame. Okay, now how many accesses I have done? 1 2 3, maybe multi-level page, 4 level means 4 pages have access. And remember, page tables are residing in the main memory. So to access one location in the memory, I am accessing 4 times the main memory to get this, come to a frame number that I am looking for. And then finally I may find that it is not there at all, then I need to page fault happens and all those things happen. But even to access every translation, I need to access all the page table, which is very very expensive, right, in terms of access. So what do I do? Can I optimize it? Yes. See, finally our aim, why are we going through all these entries? To get the frame number, right? If I get the frame number, suppose I know that for a given logical address, this is the physical address, okay, this is the mapping, but it is being done with the multiple pages accessed, and then finally I'm getting the physical address. Now why not I keep this frame number, not only frame numbers, the last page table, okay, which is accessing the main memory. If I have the page table entries of that in the TLB, a cache, hardware cache. So if I have the entries, okay, this in my case here, actually the page table is here, and I get the frame number, and then as well as other control bits I have. All this data, if I put it here, what will happen is, next if I am accessing the same page, I don't need to go through this. I will find out that particular logical address. If I have an entry in the translation lookup buffer, I get the page table entry directly. I don't need to go through multiple levels of page tables to get the PTE as well as the frame number. Okay, PTE means frame number followed by all the control bits. So it actually speeds up my accessing of, or speeds up the translation of logical address to physical address. Now let me summarize it. When I have a virtual address, I know what is the offset, so I don't need to touch this at all, because it will be used finally till I find the frame number. I am not going to use the offset at all. But remaining this value may be multiple page level, multi-level pages means I will be accessing multiple pages, and then finally I will be getting the frame number as well as the control bits of a page. Now what will I do? Those final level, last level page table entry, I copy it here, and then I map it using the entire address what I have. Entire L1 offset, L2 offset, L3 offset, whatever is there, except the page offset, remaining things, whatever the bit pattern is, I will say that for that bit pattern, okay, associative memory it's called. So for that bit pattern, I it's a hardware, okay, it's not memory based or software based, hardware, it's built-in hardware. So for that entry, if it is available, it will be comparing that bit pattern, and then a comparator will be there, and then it will give me, if it is present, it will make it say that TLB entry is hit. If I don't have a TLB entry, okay, this TLB is nothing but a cache value, okay, I may have 128 entries or 512 entries or whatever. So that many addresses I will have mapping already done. If I have previously accessed it, it will be present. So I will not be going through the entire page table and accessing them. I directly use the entry, the PTE entry that I have in the cache directly to get to the physical memory. Okay, so it is faster. So translation look aside buffer. Look aside means you turn somewhere else. It's similar to when a teacher is asking a question and then looking at the student. What does the student do? Look aside, so that you don't meet eye to eye, so that teacher looks for somebody who is looking at him or her to ask the question or ask for the answer. So this look aside is when I am asking for a physical address frame number, I need to go through all the page table. Instead of that, I will look aside and see whether do I have the recently accessed page table. If suppose if I use that entry would have been available here, then I use it straight away. I don't go through the page table at all. Then you may wonder whether page table is valid or not. Yes, this is valid because as long as that page is being accessed, I am going to be keeping it all the changes. Okay, modified bit, if it is changing, then I will set it up here. So translation look aside buffer will have the entry which is getting continuously monitored and modified. Now if I am evicting the entry, that means it's only limited number of entries are there. Suppose if I am accessing some other page, I need to evict a page table entry in the look aside buffer. That means I will go update the page table, okay, wherever it belongs to, whichever process it belongs to. It should know that, and then it will update it there, so that whatever updation happened here will be reflected here. Okay, similar to dirty bit taking to hard disk, it is also taken care of. So repeated access of a page will be faster if I have a TLB entry, and that's called TLB hit. Okay, this is what is the purpose of TLB, translation look aside buffer. It actually has the page table entry cached into a hardware cache within the CPU, so that every time to get the translation of logical address to physical address, the processor doesn't have to go through the page table entries to get it. It will be available in the cache, and it's a limited number of entries. So if a new entry has to be made, if you are going through the page table and then you are getting some translation done, that will be brought into the TLB. Now, what is the algorithm you will use to evict some particular entry in the translation look aside buffer? Use LRU, because LRU is the best one. Least recently used entry, you knock it off, update the page table of that, and then use that particular entry for keeping the latest accessed address into the look aside buffer. So that when that one of the pages in one of the bytes in that page is accessed, or one of the words in the page is accessed, it will be getting that value. The translation will be done from the look aside buffer entry, not from the actual page table entries. It is much more valuable when you have multi levels of pages. Okay, so TLB, what is it? It's a virtual memory reference, can cause two physical memory accesses or much more if multi-level pages are there. So you are having a hardware cache, and it's called TLB. It may be around 512 bytes or more. Okay, in the recent processor, we used TLB entry to be knocked off when you are to create a space in the TLB, and it's a hardware cache. Okay, it has a PTE. So sequence of events, given a virtual address, processor examines the TLB first. If already entry is there, it will be used. If it is not there, it will go through the painful way of traversing through the pages, multiple pages, and getting to know the final frame number and the PTE entries. Then it will copy that into TLB now. And before copying, it should find a free space in the TLB. So it will be using the LRU to knock it off, and it will write back if there are some changes to the old entry, and new entry will be made in the TLB. Okay, that then onwards, if that particular page is accessed by the CPU, it will take it from the TLB. So when a particular process is getting removed from the core, that means all the entries belonging to that process needs to be flushed out. So TLB entry will be flushed out if I am now taking out particular page or a process from the TLB. Okay, so now that's it about TLB. Page sizes in a processors are one of them. Okay, you don't have to mug it up. It's only a knowledge. Okay, now quickly I will cover one more. I'm just want to make sure that actually this is not very important because the segmentation is not used. This is a segmentation, about segmentation. Okay, TLB recap. This is the picture. Okay, maybe if not now, later on you may need to remember at least how it is being accessed. So this is a secondary memory. Remember, though shown as it's not shown as a hard disk, but is laid out as a byte array, and this has been already explained. When you see a list of entries added to the TLB in the time order, what does each entry correspond to? Okay, suppose you are seeing them in the time order, then they all PTE elements of a particular page of the same process or different processes. It could be different processes which were accessed earlier in the same sequence. Okay, so multiple threads may be accessing, and the time ordered way of accessing the TLB entry. The order of these elements signify the order of the first access of those pages by the CPU. Okay, so whenever that particular page is accessed, the entry is made. It does not give the number of times those pages were accessed. Okay, you keep accessing it, that means the TLB entry will live there forever. If there are no free slots in TLB to add a new PTE, what will you do? You have to replace it. You have to move out some TLB entry. LRU is used, and when an element from TLB is removed, should it copy that back? Yes. If suppose there is a change in the modified bit or some access of a particular page, you have to make sure that it is copied back. Okay. So TLB flush is done when a particular process is moving out of the process CPU. That means you are swapping out or you are terminating a process. Then it may have many entries in the TLB which is no longer needed. So you can knock off all the TLB entry. That's called TLB flush. Okay. So you knock off many entries in the TLB in one go. Okay. Now one quick topic about segmentation. Segmentation is actually grouping of access permissions. Okay, all the code area, all the data area, stack area, everything is grouped together. It is size is not limited. It depends on variable size. It's like a dynamic page. We talked about sometime later earlier, sorry. So segmentation is grouping of uh, access permission based or a data code area. You are putting it together. We are not dividing into equal area. Okay, that means what? You don't have a paging system, but unequal dynamic sizes of segments you have: core segment, stack segment, heap segment. Now if suppose a program changes, recompile, the sizes of the segments will be changing. Suppose you add more data into the data area and then you recompile it, your segment size will be changing. Okay, so what happens is when multiple segments of a programs are there, you have many processes with the segment sizes of varying size. Now your main memory is going to be moving the entire segment. Okay, it's not page wise. Okay, main memory is not divided into pages. So what will happen is you will have external fragmentation. Okay, that's the main thing you should remember. It's equivalent to what we saw as a dynamic thing. So this is not actually, only segmentation was the mechanism used by Intel processor in the early stage, but right now what is being done is we use segmentation along with paging. Okay, it's not only one is being used, and each segment will have its own present bit, modified bit, and all that. Okay, we are not maintaining at the page level, we are maintaining at the segment level, and segment sizes are huge. And there will be one base address of the segment, and then offset is can be anything. So your given address is not divided equally. The offset portion will be varying. It's not fixed as what we saw in paging. Now normally what is being followed is segmentation plus paging. That means you have a segment and then divide them into equal pages. Okay, so that's what is normally used. And okay, what is the comparison? I think it's self-explanatory. You can go through it. So you have frame list or a page list. OS maintains a page table. Okay, here segment map table, and the scheme does not support users view of memory. Okay, in the paging, actually what happens is it is not residing together contiguously, right? I told you that pages can be in arbitrary way, but here the entire code will be together on the physical memory also. So it actually mimics what programmer thought about a particular segment, and they are all together here. But one more major difference is here internal fragmentation happens, here external fragmentation happens. That's all. Okay, that is not I think given here. One of these bullets, maybe you can add them also. Okay, that's it. We have come to the end of memory management. I hope this series of lectures were useful, and remember these lectures. It will be useful for the final exam also, and for your interviews and other things in the future. Bye bye. See you.